Now, 5C2 question 7. Yep, we're recording. Lions chasing a zebra. Zebra notices the lion when the lion is 40 meters away, so they start 40 meters away from each other. The lion approaches with V1 speed. The zebra runs away with this speed. It says find the speed of each animal after 1 second. I think I'll skip that because you can do that. You're just going to make your T1 in the V1 function, and in the V2 function you're going to put a 1 there as well and see what the speed is. Show the lion's speed decreases, the zebra's speed increases. So I think what you could do there is simply graph. That's what I would do. I like working from graphs anyway. So how could we graph these? These are exponentials. And obviously you could put them in your calculator and graph that way, but you've done exponentials before, so let's just think about it. If you've got your simplest exponential y equals e to the x, x-axis is the asymptote, crosses at 1, because when x is 0, you have a power of 0 and you get 1. But here I'm looking at v1, and v1 we actually have 15 e to the minus x. Not so worried about it being a minus 0.1. I'm just thinking of what's a y equals e to the minus x. What's that look like compared to the exponential that I know about, the simple one? I can use that as a frame of reference and think, well, the difference, if you go to minus powers, your x values are swapping. Your positive x's become negative x's, your negative x's become positive. So I could, from thinking about that, I can get the shape. Yeah. Now there is a difference. Obviously, we've got a 15, and we don't have minus x. We've got minus 0.1x, but I can still get this shape. The next thing I would do is see where do we start. We don't have to worry about negative time at all, right? Because we're graphing against t, time, in seconds. What's the initial speed at 0? I'd have 15 e to the minus 0.1 times 0 equals 15, because this just equals 1, right? So if I've got my idea of shape, and I know that I start at 15, and that's what the lion's doing. Okay. Let me make some room so I can think about what the zebra's doing. Okay. Now the zebra's exponential. Will have slightly different shape, because if I zero in on this bit, this minus 20, that plus 20, that lifts the curve up by 20, but what I want to do is get the shape first. The one that I know about is this, y equals e to the x, but I don't have that. I've got minus 20 e to the minus x, right? So it's like I've got, if I considered this, minus e to the minus x, I can get the shape because it matches with this one, right? What's this? V2. Right. No, not quite. I think I'm just going to delete that off the page. Right. Okay, so shapes, this is a simplified version, and shape. So like in the last one, my x's are now all negative. That's like, that has this effect. All your negative x's become positive, positive become negative, you get this reflection. So that's what a y equals e to the minus x looks like. But then we've got a minus here as well. So that's going to take all of these values, all these points, and then you're going to make them all negative. So you're getting this type of shape, right? So this is for the zebra now. I could now just think of the shape of the graph as being one that comes up like that, right? Now the difference is that this curve's been moved up 20, right? And we're getting 20 times our e to the x as well. So let's just think about what happens when the time is 0. Yeah, we'll get 20 minus 20 e to the 0 equals 0. Okay, so we're going to start at 0. Now you can see there's going to be an upper limit. Like in this shape, the upper limit's the x-axis, but what's our asymptote for our function? What we can do, we can say as time tends towards infinity, what happens to this function? So I would be getting 20 v of t would start equaling 20 minus, if I write it like this, e to the very large number. You're going to get, so what I've done is I've written that negative power as a fraction to help me visualize this. So t is going to become really, really large and infinite. We're going to be doing 20 minus 20 divided by some huge number, like a billion or something. And what's going to, it's like how many billions in a 20? Not very many. This is going to approach 0. So what's going to happen is your velocity function will tend towards 20 because this bit here will get very close to 0. So that means that that's your upper asymptote, and I think I've got enough information now. I'm not going to put a scale on it. I just want a rough sketch. Well, I'm not going to put an x scale or a time scale. So back to my grid lines. And maybe if I can draw it off to the left so it's a bit out the way. We don't have to think about negative time. So we've got velocity, meters per second, if I'm labeling properly. I've got time in seconds. So we said the line started at 15 and came down. Where can I put the 15? Maybe here. And it comes down like this. As t approaches infinity, I didn't do that, did I? What? So as t approaches infinity, just as a check, v1 will be 15 divided by e to 0.1 times infinity, right? So this number will get more and more and more and more close to 0. It'll never become negative. You guys know that. Negative powers don't make negative numbers. So basically the lion's speed is getting closer and closer to 0 as he gets more and more tired. So that, I assume. Okay. Whereas the zebra has actually started stationary. we worked out that he started at 0, and he can get up to a maximum speed of 20. Well, there'll be a point where their velocities are equal, which is interesting. 20 meters per second, which is, I guess, pretty quick. It really is quite quick, actually, as well. It's like 70 kilometers an hour or something. Anyway, he's coming up like that, right? Or she. Okay. Now, I don't know where their speeds are equal. I haven't put in a scale here, but I would like to be thinking about some velocity values. So 15, my 0, and my 20. So that's the upper limit. We should be labeling these. So this is the lion. I've got to remember which is which. V1's the lion. V2's the zebra. So it's like the lion's running at the zebra must be standing still, and then he's taken off, right? But the good news is they did start 40 meters apart. So have we shown that the lion's speed was always decreasing? I think we have. What I would say is, you could graph it. You could say 4 times, we should just do that. For time greater than 0, we could say C graph. I don't want to start doing second derivatives and anything like that. We could say this, lion's speed. It's always going to be less than 15 from what he started at. You could also say as t increases, or I did before, I did tends towards infinity, the velocity tends towards 0. From above, or we could say at t equals 0, velocity was 15. That might be a nice way to do it. So you can say, all right, I'm going to consider, just trying to, sometimes the communication of the mathematics is the hardest part. Right. So consider times between 0 and infinity. And we could say at t equals 0, the speed was 15, but as the time approached infinity, the velocity tended towards 0.